Hi, welcome. Today we will talk about the Voyager paper, an open-ended embodied agent with large language models. In the image, you see the comparison, the benchmark between different agents. The first two are Voyager, if I'm not mistaken, yes, are Voyager. And the third one is AutoGPT, which is another LLM agent builder framework. And the other two ones are prompting techniques, React and Reflection. So we can see a drastic outperformance in terms of Voyager. This happens within Minecraft, and Voyager is able to achieve very complex skills, to acquire very complex skills. In the top right left corner we see the diamond tool, which is able to build, while the AutoGPT can barely build an iron tool. So let's see how this happens, how this is achieved. So Voyager has three components: an automatic curriculum, and I want to emphasize the open-ended learning of Voyager. So it has the automatic curriculum, the interactive prompting mechanism, and the skill library. Those are the three components. The automatic curriculum proposes tasks. The iterative prompting mechanism builds the skills. So this is like a software developer. It receives a request and it builds the skill. And the skill library is used to reuse different skills developed in the past to achieve more complex skills. So for example, we see there craft stone sword and combat zombie. So instead of combating the zombie barehanded, it uses the skill of using a sword to combat the zombie. So it's composing two skills to perform more advanced skills. And on the bottom part of the image, we see a couple important details. The first is that the environment. So the automatic curriculum connects to the environment to propose tasks that are coherent with what's feasible. And the second part is the self-verification. So when the software developer builds, I mean, it's an agent, but when the software developer agent builds the skill, it uses self-verification to evaluate if the skill was built correctly or not. So those are the three components of Boyaga. Let's go into depth. So on the right side, we see how the auto curriculum uses the environment information to propose a task. So at the top image, we see that the inventory says, okay, we have oak planks, we have stick, crafting table, stone, and wooden pickaxe. So what can we do with that? This is the part of reasoning. And the reasoning is, since you have a wooden pickaxe, you can add some stones, you can craft one stone pickaxe. So we are building something based on our environment. So that's where the auto curriculum starts, by perceiving the environment. The second important aspect of the auto curriculum is that it leverages GPT generalized knowledge. So GPT already has some knowledge about what is useful in terms of Minecraft. So it uses GPT common sense to build tasks. We can see a second example. So, and I like the second one. So in the first one, it uses exclusively the inventory. In the second, it uses the fact that we are in the river biome. And here is where the reasoning goes. Since you have a fishing rod in your inventory and you are near a river, it would be a good opportunity to catch some fish. So it proposes the task of catching one fish. And it's the final part, and this is not shown in the image, but it's part of the paper, that it documents the prompting mechanism to propose tasks. And there are two key requirements on this. The first is, don't be too ambitious. Like, moderately complex task. And the second key component is that it says, and for that it uses a stream of previous interactions. So it has to go progressively more complex, but without big jumps in complexity. It also incorporates the failures and the successes. And the second part that the prompt, the auto-curriculum prompt contains is that it suggests to be reusable, so that it incorporates the intent within the prompt. I think we will cover this more in depth in the past. So now let's look at the skills library. And here is where we say generic and reusable. These are the guidelines for code generation. Generic and reusable, because the skill library will be used, as we saw in the sword and zombie example, will be used to reuse them, to compose skills from an initial skill. So this skills library, the first characteristic is that it's stored in an embeddings database, which allows them to be reusable and modular. So before building the next skill, it can fetch relevant skills. So maybe the software engineer agent can start before building, retrieve the relevant skills and decide if one of those skills is useful for the task or not. So that's where the skill library is useful. It saves work, and it accelerates progress consequently. Second, it's iterative programming, incorporates execution errors and reasoning prompting. This in particular is chain of thought. So the part of iterative execution errors, it's okay, we noticed that there was a self-verification component. So here the important part is that when it fails, it can learn from its mistakes. So that's the part of iterative programming. It incorporates the execution errors, and it also uses a layer of reasoning. It's not, okay, do this. No. Chain of thought contains examples of how to use execution errors to solve mistakes. So it has a reasoning process. So, for example, if I'm getting this execution error, the reason might be that I'm doing this wrong and I'm missing maybe this validation step, or maybe I'm missing this intermediate step. And that's where the chain of thought is. It teaches the software agent, how to use those skills how to use the errors into overcoming them. And here the prompting indicates the present and future intent. So it's not just build the program, build it for the future, build it for reusability. So I think that's that. We see also that it incorporates, so that's the skills level. So let's go into the self-verification. This could be seen as another agent, or a subcomponent of the software development agent. And here is what it happens. So it says inventory, and it has the task. So those are the two components of the prompt for self-verification. So the inventory says, meaning coal ore will get coal. You have 5 coal in your inventory. So the reasoning is that the task was mine 5 coal ores, and now we have 5 coal ores in our inventory. We have that the success was true. So that's the first one. And that's how it uses for self-verification. Very simple. Again, we see this interaction between the environment and the prompting. Relatively simple, relatively efficient. And once the verification is complete, the skill is first converted into embeddings and uploaded into the skills library. Very important, within the building the skill, it includes a description of the skill. And that description is the one that goes uploaded into the embeddings. And here are some discussions that I want you to present to you. Maybe you can share your thoughts in the comments, maybe just think about it. So first, any general observation or even questions that you have about the Voyager architecture. Was it clear how these three core components, the auto curriculum, the skill library, and the software development agent, coordinate for this open-ended learning? Is it clear? Do you have any observations? Very important point is that during the paper, there was an ablation study that said that around 93% of the success was due to the open curriculum. And that was the main difference in the initial chart between the other two agents, between exclusive two prompting techniques like React and Reflection, and even with AutoGPT. This auto curriculum, 93% of the success. And the skill library, we also saw it in the first image. It's about 50%. So without the skills library, it can get roughly half. So any general observations? I'm giving away the first observation that the open curriculum, the automatic curriculum, it's a brilliant insight in this paper. Maybe I guess there's a lot of questions. I cannot think of one out of my mind. Second, to which other domains can this be extrapolated? Sure, this happens in a video game as Minecraft. Initially might not be as interesting as useful, but if we think about this, can we use this for other elements? And for this, we need to understand, or it's good to understand, the key attributes that make this learning architecture a success. The first part is that there's a closed feedback loop in terms of the action and the outcome. So here we have the development of the skills and we see the outcome. And it's not only a closed loop, but it's also a very fast one. So whenever we have this feedback loop that is closed and fast, it's a good opportunity to extrapolate. And what are we actually extrapolating? Is the part of the open curriculum, of the ability to progressively do more complex tasks, and also to compose tasks from building tasks. So I think those two are the important characteristics of the architecture. And if we find other problems, other environments, and probably we can add a third one, that is that we can perceive the environment, we can extract information from the environment. If we have any of those three characteristics, then it's a good candidate to implement this. And maybe, of course, the fourth one is that we are able to interact with the environment. So this is a kind of a difficult question, but follow me, please. So besides novelty, what other policies could guide our actions? And what here we are maximizing is in learning new skills. So the success of the agent of Voyager, I don't want to call it agent because that's the next question, but the result of the success of the architecture is to learn more skills. That's how it's judged. But maybe we can have a different success criteria to maybe this agent could be only to kill zombies, and we want to kill extremely more stronger zombies. That's our whole task, or to kill the most zombies in the shortest amount of time. So instead of optimizing for novelty in terms of learning new skills, we are now optimizing for finding zombies, for getting stronger to engage with zombies, etc. So those are the different policies we could be considering instead of novelty. And here the question is, which other policies are working? I already shared one example. Maybe that example could be labeled as optimization of a specific skill. Maybe we can find a better name. And the final question, is Voyager a single or multi-agent LLM? For me, this is a matter of personal taste. For me, this is multi-agent LLM. We have at least two very clear components, two very different agents. The first one is the one that proposes the task, the second that builds the skills, and we can have maybe one or two more agents. The first being the verification, it's a separate independent prompt, and the second, the retrieval of the tasks. Maybe it's also could be a prompt by itself. The storage could also be a prompt by itself. Maybe we could have and why is this important? Because once we start thinking about software development process for such architectures, these types of individual agents, as I prefer to refer them, can be split into different teams, into different tasks, into different modules, into different software packages, increasing productivity. And they can be reusable by themselves. And that's why I like to refer to them as open-ended agents. And we have multi-agent collaboration instead of a single agent. That's why I prefer it. But and in that sense, we need a Voyager. I'm referring this to architecture, maybe as model, maybe multi-agent. We need a different name. But that's how I see it. I'm interested to see how you see it. And finally, improvements. How can this be improved? Of course, the different independent components can be improved. We can place a RAG architecture on top of the auto curriculum. Let's say that it can retrieve, we can have a library already of tasks, even if we do not know how to do it, a library of tasks. And this library is used to propose different tasks, to inspire new tasks. So that's an improvement to the open curriculum. Of course, in terms of software, they use a very simple rudimentary software development agent, but they can use existing architectures to code. The verification, maybe it could be more complex. Maybe especially the self-verification works for certain tasks that are related to the inventory, but maybe if we want, for example, to have navigation tasks, it goes into the biome. I'm not that familiar with Minecraft, so maybe that's why I cannot help. And certainly there's a ton that we could do in the skills library, including refining the embeddings, having a scoring function for how tasks are being reused, etc. But the most interesting question to me is how to actually add a new component to the architecture. That's where the core of my thought is, and that's what I invite you to think. Because we right now have proposing tasks, executing tasks, verification tasks, and modality, and a library of tasks. Is there something that's missing? And let's first split the question in two. Let's first focus on the Minecraft environment, and second, outside the Minecraft environment. I will move the second part of the question once I propose where can this be extrapolated. But maybe we can, within Minecraft, we can have a social component. In terms, Minecraft is a lot about, so we can have if there's some sort of reputation or following or live stream, etc., we can add this as a model to differentiate between different tasks. So in here, we will have an agent that will propose tasks, but we will be choosing different tasks based on a specific reward that we want, like could be social following, or could be reputation, or could be complexity, etc. So that could be a very precise, like a judgment part. I'm sure if we can dive deep in this is only an example. And again, this is why it's a discussion. I'm looking forward to your thoughts. So now, disruptive application. Here are the environments that I propose that we can start to use this architecture to more useful environments that just by itself. The first one is to build web applications. Hear me out. So we have the inputs that are usage metrics, and the outputs are new features. So we say every day, let's say every day to the agent, we will have one application and we'll say, hey, this is how our application is being used. What could we improve to maximize usage? And then this happens overnight. The agent builds a new feature. We launch it. We place some ads to drive more traffic to it. We also measure recurrent feedback. And if we see the usage improving, then we say that that feature was optimal. And we can also see how features can be composed of different features. Since we have this feature, we can enhance this feature already existing. Or we can combine these two features to add a new feature. So that's where the three parts of the components go. And we can basically automate not only the software development tasks, but even the project manager tasks. And we can even, at some point, I will show it in the next two, how can we automate the distribution? So that's the first. Second, automate data analysis. So here, this is even simpler because we have an environment like Kaggle, that it has a bunch of data sets, a bunch of tasks that are already defined, and we want to maximize the accuracy. So here we have a prompting mechanism, an auto curriculum that suggests way to evaluate the analysis. So for example, perform this pre-processing on the data set. And we have a software agent that pre-process as requested. And then we have a self-verification that runs the accuracy. Maybe instead of feeding the data originally to a learning model, a supervised learning model, we feed the pre-processed data. And we can see if the accuracy improved or not. We can register that improvement within our skill library. And in such way, we can start automating that analysis by composing functions towards a goal. And again, this works great because we have a very short feedback loop, closed feedback loop, where we can see the accuracy going up and on and off. And the final one is the sales and recruiting, or even any communication tasks. And here, the part that I want to highlight, there's a lot to say in this, but here, what's interesting about this use case is that it uses two very distinct feedback loops. One that is short and one is that is longer. So the short is, for example, if I'm recruiting an engineer, did I get a reply or not? That's the short feedback. If I'm selling something, did I get a reply from the lead or not? That's the short feedback loop. But we also have a longer loop where we can see if the person that replied was hired, or if the person that replied made the purchase, or even if they had a great long-term value. And that's why this starts to become interesting, because we are not optimizing for only a very quick loop, but also to a grand loop. And we can see how if we tie the first to the build web application, we don't need to, or we can maybe use this for the marketing part, either posting in places like Reddit, Slack, Spaces, etc., or even writing the copyright for the ads. And we can see how these start engaging together to build this. So there are a ton of very disruptive applications. It's just a matter of start building. I know I'm missing one last question. How can this be improved even beyond for some of this? To be honest, I find this so powerful that for me, even the most important question is, how can I get started building something about this? I leave it to you. Please let me know if you plan to start building something. I want to support you. I want to help you. I want to contribute. And I also want to learn from you. Thank you for listening. I was Santiago. See you in a bit.